The two methods by which we can find the forces in the member are method of joints and method of sections. This method of section, the method of joints used for finding the forces in the member of a truss consists of satisfying the condition of equilibrium for the force acting on a connecting pin of each joint. The method therefore deals with an equilibrium of concurrent forces, and only two independent equilibrium equations are involved. The analysis can be initiated with any joint where at least one known load exists and there are not more than two unknown forces present. The situation may be started with the pin here in this diagram. As you can see, we can start with the pin on the left, that is pin A, as shown in this diagram, figure A. Now the joints indicated by the letters usually designates the force on each member. The force can be designated by two letters defining the two end of the members. The proper direction of force should be evident by inspection for simpler cases. The free body diagram of the portion of member AF and AB can be seen in this diagram in the figure below, in the center. Now here it is shown clearly, or it can be seen clearly, a mechanism of the action reaction of the members. The member AB actually makes contact on the left side of the pin, although the force AB is drawn from the right side and is shown acting away from the pin. Thus, if we consistently draw the force arrows on the same side of the pin as the member, then the tension on AB will always be indicated by the arrow away from the pin, and the compression, as in the element AF, will always be indicated by an arrow towards the pin. The magnitude of AF is obtained from the equation. We can say the sum of forces acting along y-axis equal to 0, and for the magnitude of force on AB can be found from sum of forces acting along x-axis equal to 0. The joint F, as you can see, the joint F may be analyzed next. Once you have found the value of A, solve this joint, you can jump to joint F. Now, since this joint contains only two unknown forces, that is EF and BF, proceeding to the next joint having no more than two unknowns, we subsequently analyze the following joints. After F, we are going to analyze B, then C, then E, and then finally D. Now, it has to be in this particular order, as you can see from the diagram on the far right, starting from 1, 2, 3, 4, 5, and 6. Now, this figure is a graphical representation of two equilibrium conditions, that is, sum of forces along x-axis equal to 0 and sum of forces along y equals to 0. The number indicate in the orders in which these forces are analyzed, and we note that when joint D is finally reached, the computed reaction R2 must be in equilibrium with the force in the member CD and ED, which were determined previously from the two neighboring joints. This requirement provides a check on the correctness of our work. Note that the isolation of joint C shows that the force in CE is 0. When the when the equation sum of forces along y-axis equal to 0 is applied, the force in this member would not be 0, of course, if an external vertical load were applied at it. It is often convenient to indicate the tension as T and compression as C on the various member directed on the original truss diagram by drawing arrows towards arrows away from the pin for tension and towards the pin for compression. This designation can be seen in the presented example. Sometimes we cannot initially assign the correct direction on one or both of the unknown forces acting on a given pin. If so, we can make arbitrary assignments. A negative computed force will indicate that the initial assumed direction is incorrect. Now, we have to understand sometimes in certain structures there are certain redundancies. Now, if a plane truss has more external supports than are necessary to ensure a stable equilibrium configuration, the truss as a whole is statically indeterminate. An extra support constitutes external redundancy. If a truss has more internal members than are necessary to prevent collapse when the truss is removed from its supports, then the extra member constitute internal redundancy, and the truss is again statically indeterminate. For a truss which is statically determinate externally, there is a definite relation between number of its members to the number of joints. We specify the equilibrium of each joint by two scalar force equations. Now there are all 2 times J equations for a truss where J represents the number of joints. For the entire truss composed of M two force members and having the maximum of 3 unknown support reaction, then there are altogether M plus 3 unknowns. Thus, for any plane truss, the equation M plus 3 is equal to J will be satisfied if the truss is statically determinate internally. A simple plane truss formed by starting with a triangle and adding 2 new members to locate each new joint with respect to the existing structure satisfy the relation automatically. The condition holds for initial triangle where M is equal to J, where M and J are equal to 3. Now M can be increased by 2 and J will offer M increasing by 2, J will always increase by 1. Certain non-simple statically determinate trusses such as K-truss, as shown here, are arranged differently but can seem to satisfy the same relation. The equation which we have discussed before, that is M plus 3 is equal to J, is a necessary condition for stability, but is not sufficient for the stable condition, since one or more of the M members can be arranged in such a way that cannot contribute to the stability of the configuration. Now, if M plus 3 is greater than 2J, then there are more members than the independent equation, and the structure is, or the truss is, statically indeterminate internally, and there will be redundant members present. Now, if M plus 3 is less than 2J, then we have deficiency of internal members and the structure is unstable and is going to collapse under any loading. So there are certain special conditions in solving several conditions or several truss analysis. When 2 collinear members are under compression, as you can see in the figure A, it is necessary to add a third member to maintain the alignment of the 2 members and prevent buckling. As we have in the beginning of this chapter, we have stated that these equations are not here to solve the material buckling problem, but this member is here to stop buckling. And we can see from force summation that y direction, as you can see, y direction, and the force F3 in the third member must be 0, and from the x direction that F1 is equal to F2. This conclusion holds regardless of the angle theta, and holds also if the collinear members are in tension. If external force with a component in y direction were applied on the joint, then F3 would no longer be zero. When two non-collinear members are joined as shown in figure B, then in the absence of any external applied load at this joint, the force in both members must be zero, as we can see from the two force submission right here. When the pairs of collinear members are joined as shown in figure C, the forces in each pair must be equal and opposite. This conclusion follows from the force submission indicated in the figure. The truss panels are frequently cross-braced as shown in, cross-braced as shown, as I will show you right here. Such a panel is statically indeterminate if each brace can support either tension or compression. However, when the braces are flexible, this means these two interconnecting braces for two trusses, these interconnecting braces are cables. They are incapable to hold for any compressive loading. As they are cables, I have mentioned earlier, the only force they can handle is tension in these acting in these members, and they can be disregarded, and we can discard other members. It is usually evident from the asymmetry of the loading how the panel will deflect. If the deflection is indicated as you can say in the direction where these cables are no longer in tension, they are going to collapse, and the structure will not retain any rigidity. When this choice, you can say this choice cannot be made by inspection, we may arbitrarily select the member to be retained in that particular way. Now, if the assumed tension turns out to be positive upon calculation, then the choice was correct. If the assumed tension turns out to be negative, then the opposite member must be retained and calculations are to be redone. We can avoid simultaneous situation for the equilibrium equation of the two unknown forces at the joint by a careful choice of reference axis. Thus, for the joint indicated symmetrically, where L is known and F1 and F2 are unknown, a force submission in x direction eliminates reference to F1, and force submission in x prime direction eliminates reference to F2. When angle involved are not essentially found, then simultaneous solution of the equation using one of the set of the reference direction for both unknowns may be preferred.